hopefully this will be interesting and not too long-winded. So let's just jump right in. Quick sort of reminder, just so everyone's on the same footing going in, although I expect most people will already be familiar with this. We're going to be talking about sort of symmetries using the language of groups. A group is a mathematical structure with the properties here, which I won't go into point by point. And we're going to be focusing on equivariant functions, as has been sort of very popular in recent years. And an equivariant function is exactly a function where if I apply a group element first, I can actually just pull it out of the function and apply it later. So maybe one example here is, my group is multiplying by 1 or -1. My function is taking x squared, and the group on the output actually doesn't do anything at all. If I take x and I multiply it by -1, that's the same thing as taking f of x and then acting on the output, but since the action doesn't do anything, we get the same output. Maybe a more familiar example to people from the machine learning literature will be something like segmenting a scene. If I have some image and I'm trying to sort of label, here's a glass plate, fork, knife. If I then rotate the image, everything will rotate on the output in the same way. So the group action sort of commutes with the function itself. Now, something I wanted to just use this small example to point out is that sometimes the things that you're doing, transforming the input, are not invertible. So here I actually wouldn't know that there's a knife. So I can't go from this image back to this image here. And so for that reason, sometimes it's more useful to talk about semi-groups. The difference doesn't turn out to be too important, except for really one specific case I'll talk about at the very end, if we have time. But with that sort of groundwork out of the way, the main point of this talk is going to be to sort of explain a general trade-off that can happen when you're trying to do learning problems where there's symmetries, in particular where the symmetry might not be known. And one is the ability to actually approximate functions that you're trying to learn that have a symmetry using other functions that also have the same sorts of symmetries. So here, we have this function with a reflection symmetry, and we're trying to approximate it using quote unquote simpler functions. There's a trade-off between the ability to do that and the ability to actually identify which group of symmetries is present in your data or in the functions that you're looking at, just given sort of functions that are equivariant to that symmetry. So here we might have a bunch of functions that respect rotations, or maybe actually rotations and reflections, and we're not able to distinguish the two cases. The examples will become actually clear and less sort of toyish as we move on, but the general idea is there's some sort of trade-off between two things we want to be able to do, and we can't always do both of them. So a general sort of outline of what I'm going to talk about here is first a general setup of trying to learn symmetries, how we're going to think about this. And then we're going to talk about an experiment basically that I ran that motivates this work. And it failed, but it failed in a very particular way, which revealed some interesting structure and sort of reveals this trade-off as a generalization, which is what we cover in this point 3. And finally, we'll talk about why group convolutional neural networks sort of don't actually have this same failure, which is, I think, an interesting result. Along the way, there are some sorts of tangents that are worth discussing. So, for example, when running this experiment, we need to talk about or use approximate equivariance rather than exact equivariance and things like this. But we'll get to those along the way. Okay, so in general, I know this slide has a good amount of text on it, but the idea is we have a set of functions, a universe of functions that we may be interested in learning. This can be maybe just all functions from images to real numbers, something like this. And we also have a universe of groups. and we're interested in learning or picking out some group from this universe of groups. So maybe I'm interested in all groups that transform images in sort of natural ways. I'm trying to figure out which group actually is a symmetry of my data. And when I'm saying that we want to learn functions and groups, I'm basically saying we want to pick out elements of F and elements of gamma by converging to them as we see more and more data. So we're going to have a notion of approximation in these spaces. In particular, I'm going to assume we have some notions of convergence, and these can be topological notions. They can actually be a little bit more general, but for this, maybe it's easiest to refer to the paper. Basically, you want to have notions of what it means for functions to get close to the function you're actually trying to learn, or for groups to get close to the group you're trying to learn. And this last one turns out to be a little bit trickier, but maybe we'll only cover that sort of if we have time, because it gets a little bit complicated. So in saying that we want to learn symmetries, it's useful to pick out a subset of pairs, FG. And these pairs are exactly going to be those pairs where F is a G equivariant function. So we have to specify sort of how G acts on the input and output of F, but supposing we have that sort of squared away, this set R, or relation R, is going to consist of all pairs where F has a symmetry G. And we're going to try to learn points specifically here. So maybe I have F is this segmenting function that we have up here, and then the group is going to be sort of shifts and rotations in image space, because it turns out that segmenting actually transforms under that group. And so I'm going to try to learn that point in this space R. And I'm going to only be allowed to use sort of a subset of these functions and groups to actually do this learning. And the subset might impose sort of relevant constraints or hypotheses that you care about. So for example, you might only be allowed to use neural networks as your function approximators. You might only be allowed to use sort of certain groups, or the groups might have to relate to the structure of the neural network in a certain way. But the results that we talk about will sort of be pretty agnostic to the specifics. But to make this concrete sort of in a picture, it's I think easiest to see it this way. Let's say we have functions sort of cartoonishly drawn on this axis and groups on this axis. And this set R is sort of all the equivariant pairs, we might call them. And what we're actually allowed to do to use in learning is the set A. And so what most currently popular machine learning techniques do when they talk about using symmetries is sort of this picture here. They say, let's fix a group G. Maybe this is translations, and I'm talking about convolutional neural networks on images. And I'm trying to learn some function F using convolutional neural networks. So I start with a function F1, I iterate my learning procedure, and eventually I'm going to converge up to a function F. Now note that F actually might not be in A, it might be sort of in the closure of A, strictly speaking. But the idea is that I'm using group convolutional networks to converge to some function which might not itself be a GCNN, but that's how I'm learning with a fixed symmetry in mind. Now we want to say something a little bit more general. We want to say, okay, let's start with some, initial group and initial function, but we actually want to be able to learn both at the same time. So that's sort of where we want to be if we're going to be learning the group instead of just imposing it a priori. And just to I guess, put on the table some terminology that's going to be useful a little bit later. Sort of if we project the set A, or the closure of the set A, onto the f-axis, this is sort of what are the learnable functions using our class of neural networks or whatever we're looking at. Similarly, if we looked at just the projection on gamma, that would be the learnable groups. This is the general setup. Maybe it's good to stop here just for questions, because I think this is sort of conceptually the main setup before we move on to details.
What kind of toy example should I have in mind thinking on a simultaneous approximation? Do you have
what, sorry?
What a toy example, what should I have in mind thinking on when doing a simultaneous approximation? Do you have any?
So, for example, right, maybe you have a lot of images and you sort of know that there is some sort of space symmetry in the function that you're trying to learn, or maybe multiple functions that you're trying to learn. Something to point out here is that actually if you're using only one function, you might not actually learn the general group you're looking for. You might need to see multiple functions to pinpoint the exact group. But say you have sort of data sets of images, and it turns out that they are all sort of horizontally shift invariant, but they aren't invariant under vertical shifts. In the functions that you're trying to learn on. But you want to be able to learn that from the data. You don't want to necessarily have to look at the data yourself to be able to figure that out. Or yeah, I don't know if that's a satisfying example, but something.
Yeah, thank you very much. Yes. Okay.
I also have a question.
Yeah.
And do you just learn the group, or do you learn the group with the two actions on X and Y?
Yeah. So this is a good question. Actually, whenever I'm talking about a group here, I actually mean a group with the actions already specified. So these are sort of concrete groups, not groups in the abstract. But yeah, that is an important point. Okay. So something to think about also when we're talking about how we're going to learn symmetries is actually how do we design these neural networks. So one broad class of ideas that sort of I think is kind of classical at this point is you fix some class groups gamma that you're interested in. So for example, these space groups acting on images. And then if you're interested in having a network that's equivariant under a specific group, what people usually do is they say, okay, I'm going to have a G-equivariant linear map, and then a nonlinearity that's sort of universally equivariant under any group in gamma. So this is exactly how group-convolutional neural networks work. Gamma is space groups, and the nonlinearities are just any pointwise nonlinearity one will be equivariant. So yeah, you can see sort of this being used in trying to learn symmetries actually already in sort of these papers here. But yeah, there is sort of a general problem, which is if gamma is too large, no non-trivial nonlinearities exist. So if gamma is, for example, sort of all groups acting on the input and output space, the only possible nonlinearity is the identity. Sort of more sophisticated and interesting versions of this observation also exists in the literature. But for us, we'll focus on sort of one particular version of how you might do this, and this version, gives us interesting experimental results. So this is based on work of Mark Finzi and co-authors at NYU. The Equivariant Multilayer Perceptron, or EMLP as they call it, layer basically has the same pattern that we mentioned above. You have some sort of matrix W, but you say, okay, let's make this matrix equivariant in a certain way that we'll get to shortly under the specific group G you're interested in. So you get W tilde, which is equivariant, and then you have a nonlinearity, which will sort of be equivariant to any sort of group that you pick, as long as sigma sort of respects the way that the group acts on your input and output space, and sigma will be based on sort of scaling and tensor contractions. But that's sort of not the main point here. What we'll be interested in is the fact that, yeah, we have a linear map that is made equivariant. And in particular, the way that this happens is it's projected onto the subspace of equivariant maps specified by generators of the group. So if I'm interested in making the linear map equivariant to rotations, I'll basically just specify a single Lie algebra generator of rotations, and then I'll be able to project W to W tilde. And in general, they have this written down in a nice theorem, but you can sort of see without too much difficulty that W tilde will exactly be sort of projecting onto the null space of a particular matrix that you can write down in terms of the group generators. So this leads to a sort of pretty natural idea, which is, okay, if I want to learn the group and my function, my neural network simultaneously, maybe I can just learn the generators simultaneously with sort of all these free parameters, W, that specify the weights in my linear layers. Yeah, so, what happens when we try to do this will specifically be the result that we look at. But before we get to that specifically, there's sort of a little thing we need to take care of, and I think it actually turns out to be sort of fundamental, but I didn't realize this when I tried to run this experiment at first, which is you need, I think, approximate equivariance if you ever have hope of learning a group. So what I mean by this actually is sort of, if we go back here and say, okay, we're going to learn G and always make W exactly equivariant to whatever we think G is in this stage of learning, we're going to run into problems. Or sort of being too optimistic and saying that at each point we think we've figured out exactly what the symmetry is. So one way of seeing this in this particular case is that this matrix whose null space we're going to be taking actually usually has trivial null space. You can basically say with high probability most matrices have trivial null space, but you can also make some sort of formal statements, which I won't go into too much detail here, but I'll leave them here for posterity if people are interested. I think more intuitively, you can sort of just draw a picture and see that something will go wrong. So suppose that we're sort of interested in the group G sub epsilon, which is like the rotations, but sort of generated by the perturbed generator of rotations with these little epsilons there. If epsilon is greater than 0, then the orbit of a certain point is going to be a spiral. And as epsilon gets closer and closer to 0, the orbit gets tighter and tighter until suddenly it becomes a circle. So, maybe one way to think about why this is a problem is if you look at a little patch around this point, maybe your data sort of lies here. There it looks like, your function, if it's to be invariant, say, to these rotations, you don't have too much constraint on what your function is, although it turns out that you do. But if you drive epsilon to 0, suddenly you're getting more and more points that are on the same orbit and thus have to have the same value under this function that you're learning. And so as epsilon becomes closer and closer to 0, your function actually, intuitively should become a constant. And so if you're saying, I think my symmetry is exactly G sub epsilon, you're going to never be able to drive epsilon exactly to 0. So you maybe want to say, I'm allowing some relaxed notion of invariance or equivariance in the function I'm learning, so that along the orbit, I'm not forced to take exactly the same value. So maybe here is also, again, a good point just to check if anyone has any questions. Okay, seems like we're good. But okay, I won't actually discuss how we address this. It becomes a little bit technical. Maybe I'll mention it if we have time at the end. I have one slide that we can go over, but the main point is just that, another sort of quote barrier to learning symmetries is actually, I think, this approximate equivariance, which has not been studied too heavily, at least so far. Okay, so let's look actually at what happens when we run this experiment. So suppose that the true group we're trying to learn is the group of permutations of 2 elements. And actually, I'm going to use some sort of simplified nonlinearities. I didn't mention what the nonlinearities actually are, but just to be honest, we're not using sort of the tensor contraction part of the nonlinearities that Finzi and co-authors use in their paper. If we do use it, then actually the experiments don't converge at all. So there's something still to work on there that I'm thinking about currently. But if we use these simplified nonlinearities, there's sort of 2 regimes that we can fall into. And we're trying to learn a function f that is G equivariant. So if f is nonlinear, we actually don't learn f at all, unless the group that we sort of get out at the end, the machine learning algorithm is sort of saying this is the group that we learned is trivial. And in fact, we should note that the trivial group is always a solution. So any function is equivariant under the trivial group. So to avoid this case, we actually basically should impose some priors or regularization or something like this. This is also actually sort of a fundamental thing that you need to think about if you're trying to learn a symmetry, is how to avoid the case that basically say, yeah, there's no symmetry, and that's always a valid answer. If we do impose some sort of priors and sort of try to avoid this, then if f actually is linear, we end up being able to approximate f correctly, but we don't learn the group. And instead we learn something like this, that the group that we think is present is just all matrices of this form where we have A on the diagonal and B on the off diagonal. Now, when I was running this experiment, I ran this multiple times, and this always happened in sort of different variations, even if you use different groups. You have sort of a structured matrix that seems to relate to the true group, but it's not the true group itself. It's substantially larger. And it turns out that this is exactly sort of the group algebra of the group. You can sort of formally define it in terms of functions on the group here, but really you can just think of it as linear combinations of the group elements. So here we have linear combinations of the two matrices. And it's not too hard to see intuitively why exactly this happens. Basically, it's that a linear map is G-equivariant exactly when it is RG, or equivariant under the group algebra. And it's sort of just these two equalities that you write down here. So really, linearity is sort of the barrier here. We are looking only at linear, or we're trying to learn linear functions that have a certain symmetry, but linear functions aren't enough to pick out the correct symmetry. Now you might ask, why we learn the algebra rather than some even larger structure. Maybe the things that the symmetries of these G-equivariant linear maps can be even larger, but it turns out that actually RG is the right structure in a certain way. It can't be any larger. For more details here, I think, again, it's probably easiest to refer to the paper, but basically for semi-simple groups, you have Schur's lemma and Jacobson's density theorem, which imply that RG is the biggest thing. And this generalizes even to sort of more general cases, and in particular in cases when W isn't a map between sort of the same input and output space. You have sort of the layers of a neural network are mapping between different spaces. You can say something similar to this sort of result.
Sorry, one question.
Yes.
Can you say something about the case if f is nonlinear? Why does it learn this rubbish G? I mean, that's not what you would want, right?
Right. So this is a very good question. This actually is sort of explained, I think, more easily in the general result, which this motivates us to look at. But there's exactly this problem that, we either are, maybe this actually isn't, maybe it'll be better to return this question after we see the main result. But the point is that, if we abandon linearity, then sort of the structure of the network and the way that it is able to identify groups doesn't work out. I realize that's sort of hand wavy for now, but I think maybe with the generality it actually becomes clearer. Also, the point is not that we can never learn a nonlinear function, just to be clear, right? If we allow the neural network to say, actually, I think the group is trivial, then it's just any old neural network, and of course, we'll be able to learn the function. It's just when we try to learn the function and the group at the same time that we run into problems. Yeah. Okay. And so just to draw a picture that sort of explains maybe what's going on above in a little bit of a more satisfying way. If this big egg is all functions f from x to y, and we're saying, okay, we're only going to focus on linear functions f, then on the set of linear functions, the functions that are G equivariant and RG equivariant actually are exactly the same. So if I'm only allowed to see linear functions, and I'm told these linear functions are equivariant under the structure that you're interested in, I can't distinguish between R, G, and G. If I'm allowed to look at nonlinear functions, of course, I will be able to witness that R, G, and G are different, but somehow we're noticing that we're actually not able to do learning properly in that setting. Now, also, there's some other reasons that the experiment above by itself is not completely satisfying, which is if we're drawing this picture for linear maps, well, that's not super interesting because linear maps can't approximate any larger class of functions. So I want to understand sort of, how does this picture actually explain maybe the slightly more general setting of the experiment, which is I'm using nonlinear maps to do my learning and trying to learn functions that are not linear maps. And also here, there's no discussion of, there's no discussion of G changing as I'm doing my learning, which is something that's happening in the experiment, right? I'm modifying G during the training iterations. And so maybe something would happen if I'm actually allowed to approximate G rather than identify it exactly, but it turns out that, this happens in sort of the approximating sense as well. And this is exactly what we see in sort of this main result, which we'll talk about now. And the term we're going to use here is symmetry non-uniqueness. And just to tie this in immediately with what we've seen before, the idea of symmetry non-uniqueness is basically related to this fact here, which is linear maps that are G equivariant are actually all also RG equivariant. And in fact, it goes the other way as well. But there's sort of a non-uniqueness in the symmetries of G equivariant linear maps. So to make this slightly more general, a symmetry non-uniqueness is a map between groups within the universe of groups that I'm interested in, which sort of preserves equivariance with respect to the hypothesis class that I'm allowed to use. So for linear maps, this was just linear maps, and going from a group to sort of the group algebra. Actually, it would be the smallest group contained in the group algebra because here I'm mapping between groups exactly, but that's not really the point. In general, it's basically saying, okay, suppose I have an equivariant pair, so a neural network maybe, and a group that it's equivariant for. A non-uniqueness is a map that modifies what the group I'm considering is and says that actually the neural network is still equivariant under this new group. Now notice that this new pair doesn't have to be in the hypothesis class, namely the group HG doesn't have to be sort of a group that I'm allowed to represent with my learning algorithm. It just needs to be something that is still an equivariance of the neural network.
Sorry, Ian, can you mute yourself? There's some background noise coming from you. Sorry for the interruption.
Yes.
So to make this concrete, maybe I'm only allowed in my hypothesis class to use discrete groups or finite groups, I should say, like the permutations that I used up here. But this sort of non-uniqueness is no longer a finite group. Here, there's infinitely many matrices here that these W tildes are now equivariant under. So it's no longer part of my hypothesis class of things that I could possibly think the symmetry is. But nonetheless, when I do this, I get something that still is a symmetry of the neural network. So this is sort of the definition of symmetry non-uniqueness. And it's maybe easiest to, again, see sort of in the diagram here. I'm just saying that if I start in A and do H to change which group I'm considering, I will always stay inside of R. And as I should mention, we assume that R is closed, but this is sort of a mild assumption. Closed with respect to sort of the convergence that we consider in here. So now we have sort of the two main results, and actually it turns out that these results are fairly simple. I think if you draw these pictures, they become obvious, but the point is that they're interesting within this context of learning that we're thinking about. So first is if H is continuous at a particular group G that we're interested in, and F is G equivariant, but not H of G equivariant, then FG is not learnable. Okay, so what does this mean, maybe? Let's say that H is this map that we looked at above, taking a group to its group algebra, and F is the function xy, which is x squared plus y squared. This is permutation invariant. But if you do a little bit of algebra, which I won't do here, but basically you can trust me on it, F is not going to be invariant under sort of the natural action that you would use for the group algebra. And this actually means that F is not learnable using sort of the neural network ansatz, or the neural network hypothesis class that we were using before. Exactly because every neural network is G equivariant, and therefore it is also H of G equivariant. And thus every function that the neural network can approximate is also H of G equivariant. And so since F is not H of G equivariant, it's not learnable. And that is actually basically exactly sort of the proof that we have done here in the more general case. Okay, but now we can actually say something that I think is a little bit more interesting, which also has to do with whether or not we can figure out what the symmetry is by looking at that multiple symmetric functions. But we need to add a couple of extra hypotheses to be able to do this. So first is that H of A is actually a subset of A. So what does this mean? This is something like saying that the neural network class I'm using, together with the groups that I'm allowed to represent to be equivariant under, is actually expressive enough. So before we said, okay, maybe the groups I'm allowed to use are finite groups, but H can take me to things that are not finite groups. Here I'm actually saying no. Let's suppose that we're general enough that we're allowing all the groups that H can take us to from A. And then this slightly harder to interpret assumption that R is a subset of H of R. This is something like saying that H is like taking a supergroup of G, so that when you take H of G, you're sort of imposing more symmetry than you had before. Is the best way I can try to explain what this means. And then we have again the same sort of assumption that H is continuous at G. When we have all of these together, we have exactly the trade-off that I was mentioning at the beginning. Namely, not both little I and little double I can hold. Now, what are these two things that are both desirable? First is that if we have a learnable function, meaning that, just to remember, it's sort of on this part of F. So there is some neural network that can learn this function. Maybe it's a neural network where I assume that the symmetry is trivial, but there is some neural network theoretically that learns this function. And this function happens to be G equivariant, that actually the pair FG is learnable. Meaning that, okay, maybe I could learn this function without assuming any symmetry, but what I want to be true is actually that I can learn the symmetry and the function simultaneously. So I can figure out what the symmetry is from data and approximate it, and also approximate the function at the same time. This is clearly sort of the point of what we were trying to do in the setup of our learning algorithm, of our learning problem, sorry. And the way that you draw what actually this means is that A sort of fills in R horizontally. And this is sort of like a local universal approximation statement is a way to think about it. I have learnable things, but actually the symmetric things are learnable with the symmetry together. Yeah, the reason I mentioned that it's like a universal approximation statement is actually because filling in horizontally is sort of like a dual to filling in vertically, which is exactly what universal approximation for a specific group looks like, right? If I have a particular G here, and we say, convolutional neural networks are universal, it means exactly that anything in R any equivariant function is approximable within using group convolutional neural networks. But here we're sort of going the other way. Okay, maybe that's actually not super important, but we have this first sort of local universal approximation statement that we want to be true. Now, the second part is about being able to identify the symmetry in the problem. So in particular, what we want to be true is that there is some learnable function which distinguishes between G and H of G. Sort of witnessing this function and learning it together with the symmetry will sort of let us be able to distinguish whether G is a symmetry or H of G is a symmetry in our learning problem. So the idea would be something like this. We have F, which is G equivariant right here, but then H maps us out of R. So basically this point FR, FH of G is not in R, meaning F is not H of G equivariant. And this sort of function F then witnesses that H is not a symmetry of the data that we're trying to learn. So we're able to distinguish between G and H of G. Okay, so to recap, we have these two things that we want to be true. We want to be able to simultaneously learn functions and groups, but we also want to be able to correctly identify which group is the symmetry of the function or multiple functions we're looking at data from. And under certain conditions, we're actually provably not able to do so. Either there will be sort of, and the conditions, right, are the existence of this non-uniqueness map H that has certain properties. So if you design your neural network such that taking H means that the functions that the neural network represents are still equivariant under H of the group that you're thinking of, you'll have this problem arise where either you don't have this local universal approximation, or you won't be able to figure out whether H of G is a symmetry that you're looking for or not. Okay, so this is sort of the main result. There are a few things that are interesting to get to, but I think maybe here would be a good time to, again, just check whether there are any questions. And yeah, for sort of the proofs, I would direct you to the paper. Okay, cool. So hopefully that wasn't too confusing. I get confused myself sometimes when I explain it, is the reason I mention it, but hopefully it's clear. We have a trade-off, but it only happens when we aren't careful and specify a neural network that has this H non-uniqueness. Okay, so there is something that we can talk about, which is, I never mentioned what is the notion of convergence here. We had this picture of functions approximating another function, or we have a group here and we're interested in what it means for a group to approximate another group. These become somewhat technical, but it turns out that for most ways that you could specify approximations of functions and groups, as long as they're compatible in a sort of natural way, this problem arises. But it is important to understand that you need to specify what notion of convergence you're interested in. So for functions, it might be, uniform convergence on compact sets is the common universal approximation notion that people use. And for that, there are sort of compatible notions of approximation of groups that you might be interested in. So just to sort of maybe say a little bit about it, I probably won't want to go into too much detail, but if we have our functions from X to Y, we're interested in groups that act on both X and Y. So we're interested in subsets of the paired transformations on X and on Y. And we want to have a convergence which is quote unquote admissible, which means exactly sort of a compatibility with the notion of convergence on functions. And then now this is a notion of convergence of specific transformations. So like a bunch of specific rotations converging to another rotation. We're interested in convergence of groups themselves. So we first specify a convergence for the elements, and given a convergence for the elements, we can then specify a convergence of sets of those elements. And there's sort of various ways you can do this, but the important thing is that it should respect convergence of the elements themselves in the following sense, which is that if GNs converge to G, we want it to be the case that for any specific little g in the group, there are actually elements within the GNs that converge along the way to that thing. And there's various options for how you can specify this. Two sort of classical notions of convergence of groups by Thurston both satisfy this, but the point is basically that these things that need to be true are true sort of in the natural cases that you would consider. I'm also happy to come back to this point later if people have specific questions on this, but I think maybe it's more interesting for the audience to move on to the next point, which is group convolutional neural networks actually don't exhibit symmetry non-uniqueness. So I mentioned at the beginning sort of two papers that use group convolutional neural network type approaches in trying to learn symmetries and functions at the same time. And it took me a while to figure out why this sort of apparently bad trade-off result doesn't apply to their experimental findings, and it's exactly because they're sort of the convolutional type. So to set up what this result means, I'm going to sort of say something general about the group convolutional layers themselves. So the layers consist of what I'm going to call integral operators between sort of signals on some input space and signals on the output space. So you should think of maybe X as a pixel grid, F is pixel intensities, L is a linear map to some possibly other dimensional pixel grid Y, and we have new pixel intensities here. There's a transformation between signals on spaces. And in particular, it takes a certain form, which is this integral form here. Integrating against a kernel function or a filter is often the phrase people use in sort of more vision-focused literature. And we're going to be considering integration against a measure mu, which is invariant under the group G that we're interested in. So in the case of images, this is just Lebesgue measure and its translation invariant. Yeah, and we're interested in translation invariant operators on images. Okay, so now we have sort of a fact, which is also, in fact, a version sort of these like convolution is all you need theorems that you see around the literature. Although the way that it is maybe not immediately obvious, but it's that if you have a mu preserving transformation on X and then a corresponding transformation on Y that you're interested in, an integral operator is sort of equivariant under this pair of transformations if and only if the kernel is equivariant in this sense here for mu almost every input that you can care about. And yeah, this basically comes up in proving this result here, which to set up we need one more thing. So sorry, yeah, this part gets a little bit confusing, but I think the result is actually worth just the small setup, which is under certain conditions. So for example, if G is compact, mu decomposes a product of our measure and a measure on orbit space. And so then you can write what L does to a function. So first of all, you can write your input as G times the orbit space. So every point X, every point Y here, I can think of as the group element and then what orbit it's in. And you can basically just write this same equation up here in terms of some function L, which depends on the kernel, but because the kernel is invariant, in the sense that we said above here, we can sort of remove one of the things and one of the arguments, and we get this function L, which depends only on 3 arguments. And we're integrating against a measure on the orbits and a measure on the group. And so this is actually a generalization of sort of the classical group convolution you see in convolutional neural networks if you sort of forget that the orbits are here, because those are for homogeneous spaces. Anyway, the point being that once you sort of do all this setup, under certain conditions, if mu is to be a measure that is also h of g invariant, the following 2 things are equivalent, which means that there's no symmetry non-uniqueness. First is that any g equivariant integral map L from signals on one space to signals on the other space is h of g equivariant. So this means exactly that there's a non-uniqueness. If you're g equivariant, then you're also h of g equivariant. This is equivalent to h of g actually being essentially a subgroup of g. So the point being that, supposing I had some sort of map h of g, which could potentially be a non-uniqueness and therefore make me unable to actually pinpoint exactly which g is the symmetry of my problem. It turns out this h will necessarily be just taking a subgroup of g. So in particular, the largest group of symmetries that I'll be able to identify is actually the correct group of symmetries. Okay, yeah, so I apologize, maybe the explanation here was a little bit confusing, but the point being that group convolutional neural networks actually don't exhibit these sort of learning problems that we have above. But the way that they do this, to be clear, is by specifying some sort of extra structure, right? We're only interested in groups that act on signals, and they act on signals in a certain way. If we become more general, then that's where problems arise. But group convolutional networks have enough structure to avoid these problems. Okay, and just to mention maybe one last thing, it's that here we have group convolutions, but if we use semi-group convolutions, for example, as explored in this paper by Maxwelling and Worrell, problems can still arise, actually. I'll just leave this here for people who are interested in looking at it later, but I mentioned at the beginning, that groups and semi-groups sort of are generally interchangeable in this discussion. This is one case in which you have to be careful, just to point it out. I think it would be sort of, a disservice not to mention this. Okay, so this is basically what I wanted to cover. The moral of the story, maybe not as clear as it could be, but I'm happy to answer questions. The moral of the story is, when you're designing a model, or maybe more specifically a neural network, which has a group that it can be equivariant to, and you want to be able to learn the group and the neural network at the same time, you should really be careful about whether your neural network has symmetry non-uniquenesses. Because if it does, then you're likely to run into these problems. And yeah, you can impose maybe strong priors about which groups are the correct groups, and then of course you might learn the correct groups if your priors align with your data correctly. But if you want to be really agnostic about which groups you're trying to learn, then if you have non-uniqueness, you're going to have a problem. And then also, right, if you're actually going to go out and do this, you should probably keep in mind that approximate symmetry will be necessary. You can't, I think, just say, this is exactly the symmetry that I think is in the problem while you're actually doing the learning. You have to sort of have approximate symmetry that maybe then you use relax less and less as you're more and more sure that you're learning the appropriate group. Great, so that is what I wanted to share today. I'm happy to answer any questions. And of course, if no one has any, I'm happy just to end it as well.